So welcome everyone to this webinar on failure and fatigue crack propagation analysis with Marc. This talk will focus on things we can do with Marc related to failure and fracture. In the area of fracture mechanics, what we can do with Marc today is to calculate energy release rates, G, and stress intensity factors, K. Basic quantities for fracture mechanics. We can grow cracks automatically, and we can initiate cracks automatically. We can also model delaminations, where we can have interface elements with cohesive zone models, material models, and also do that automatically. We also have procedures for damage analysis, progressive failure, metal damage, concrete cracking. The items in red I will not cover in this presentation. So first, a little overview over these items, what we can do with Marc. So if we start with the calculation of the basic fracture parameters, G and K, we have two methods for doing that. We have the VCCT method, virtual crack closure technique. And we can also do a traditional J integral calculation with a domain integration. These methods are available for most of the relevant material models, elasticity, plasticity, rubber models, etc. All types of elements, solid, 2D, 3D, shells for VCCT, 3D solids, I mentioned. The primary quantity we calculate is G, the energy release rate. From that, if we have a linear elastic material, we can just calculate the stress intensity K from these G's. So these are the basic fracture methods we can do. If you go into crack propagation, it comes in two flavors. We can do fatigue and we can do direct crack growth. And for fatigue, we do low cycle fatigue and high cycle fatigue. And just some information on what we mean by that. With low cycle fatigue, we have a small number of cycles, so up to 100 or something like that. So we can model each and every load cycle we have. So we do a load cycle, say a loading, unloading, and then we grow the crack. And then we do another loading, unloading, and grow the crack. And what you want from this type of analysis is typically you want to find which way the crack grows. In this case, you have two cracks and they follow a certain path that we want to find. And if we have a 3D crack, we want to see the shape of the crack as it evolves. And you also typically want to see G or K or both as a function of the crack length given the path that we have. So this is typically what you want to do in a low cycle. And the key thing with this is you do the load cycle and you grow the crack. Typically, you specify how much the crack will grow. So you define your load cycle and you define your growth increment. So you load, unload, grow the crack, load, unload, etc. And this is what is done in this particular example. And here we do a simple tension, loading, unloading. If we would say shear this one, we would get a completely different crack path. So the path we get is of course depends on the loading. In high cycle fatigue, we can have thousands or millions of load cycles. We can't model every one of them. We don't want to model every one of them. It's just one is very much like the other one. But we really want to deal with the high cycle portion of it. So what we do then is we model the representative load cycles. So if you have thousands of loading, unloading, maybe we model 50 loading, unloading. And then we could calculate the number of fatigue cycles using a fatigue law like Paris law. And the Paris law is the one we use in Marc today. And the results you want to have from this type of analysis is just like for low cycle fatigue, you want to know which way the crack goes and the shape of a 3D crack. But you also want to find the number of fatigue cycles as a function of the crack length. So curve on the lower right, you see that for a growth length of 5.5 millimeter, or whichever unit we have, it took something like, 350,000 cycles to grow that length. And that's a typical result you would want from this kind of analysis. If we go for a direct crack growth, it's different type of analysis. We have a transient load typically. In this case, we're just pulling this one up to the left, I think, a little. And we have a crack, and we grow it only when the specified growth criterion is fulfilled. So before the growth criterion is fulfilled, nothing happens. And when it's fulfilled, then we grow the crack. And a simple type of growth criterion is simply that the calculated energy release rate is larger than a growth resistance or fracture toughness, which is typically a material parameter. And what you want to see here is you want to see if the crack grows, and if it grows, which way it takes, which shape a 3D front will have, and how far it will grow for a given load. In this case, we do it in, like 50 increments or something like that, and it grows a little bit for each growth increment. And that's part of what we want to analyze. Moving on to crack initiation, you can always create your model such that it has a crack in it. When you start in the pre-processor, you can model it. You model the crack if you want, but this allows you to have a model which doesn't have a crack at all from the preprocessor. And what you do is you define where the crack should be located, and then the actual insertion or initiation of the crack is done inside Marc. And you can do this before you start the analysis, or as you start the analysis, or in a load case. So we can do a certain preloading without cracks, and then you insert cracks, and then you continue analysis with the cracks. You can do a preloading, initiate cracks, and do a fatigue analysis, for instance. That's what you can do. And typically what you want to do this for is you want to check what happens if your cracks are at different locations. You have your same base model. You say this crack is here, let's move it 5 millimeter, let's add 4 more cracks, etc. So you can experiment with that without having to do major changes to your model. You can also use a criterion, we'll get to that later, where we will insert a crack based upon the solution. Which is what we do with delamination growth. You can see that as a special case of crack growth, if you like. So suppose you have a composite structure, you want to see what happens if you get delamination between layers of the composite. You would model each layer with elements, but you don't know where it will occur. So you just have this model without double notes or anything like that, and then we have a stress criterion which says when this is fulfilled, you split the mesh. And when we split the mesh, we can insert interface element in the split, or we can activate the crack growth. So we can see that as a way to do crack initiation. And it's all automatic, which is a key thing. You don't have to prescribe up front where it's going to happen. And you do this if you want to study delamination as material interfaces, for instance, or just want this as a way to initiate a crack. So with that, we go into more details about these processes. When we do crack growth, we need to change the mesh. And in Marc, we do not use procedures like XFAM or similar. Instead, we explicitly change the mesh in various ways. So this is the first, maybe simplest way. We can update the mesh in order to grow a crack. So we're using glued contact. So in this case, we would glue the stringer to the skin, and it's the boundary where we glue and not glue that defines the initial crack. So in this particular case, we pull them apart, and if this is a direct growth, when the growth criterion is fulfilled, we release the glued contact, and we change the glued contact to regular contact. So this can do regular contact with sliding. This is useful if you know where the crack is going to be, because it will always be in the contact interface. And sometimes it's very convenient to glue these parts together. You don't have to match up the meshes in this case. You don't even have to have the same element types. The skin in this case could be modeled with solids, and the stringer with shells, and you glue the shell to the solid, and you still can do the crack growth in that interface. So this is an example of a skin stringer delamination. Second method, we can split the mesh at element edges and element faces. So you start out with a mesh which has fully connected. You don't have to specify any double nodes or something like that. That you would do, of course, for contact, because then it's separate parts. And then you split up the mesh automatically as the crack grows. So you have a crack here. You have two crack fronts to start with, and when it grows along, in this case, an element phase or many element phases, and you add nodes and change the topology of the elements in order to create the cracks or grow the cracks. Also here, it's typically used when you know the crack path. In this case, we know it's going to happen between these two parts, a T-shape and a base plate, all with solids. So we can force it to grow in an material interface. You can also force it to grow at an interface between element sets. So you can force it to take any which way you want. You can use this for general growth directions. If you have a mesh of tetrahedrals, fine enough, and you can have different growth directions, but the growth is always restricted to be along element phases in that case. So it's typically used when you have a known crack path. But the shape of the front, like we see here, can change. It goes from straight and the front is curved, but it does not go out of the plane. Third method, the most general one, where we use the global remeshing feature in Marc. In this case, we create a completely new mesh, and then we transfer all the data from the old mesh to the new mesh. So we use like plasticity, the plastic strain will be transferred from the old mesh to the new, so we preserve that. It's a nonlinear analysis. And during the remeshing process, we update the cracks, which gives us full freedom to change direction, go around corners and everything. So it's designed to deal with complex geometries and general growth directions. So it will calculate an estimate of the growth direction and update the crack to model that. The relatively new adaptive remeshing technology in Marc we have allow us to focus the meshes around the crack. So you see here that the fine mesh always follows the crack front as the crack grows. And then next step is that there are some important aspects of crack growth that we want to be able to model. If you have multiple cracks, they will not grow at the same speed typically. You have one with a high load and one with a lower load. The one with a higher load will grow faster. So what we do in order to model that is that you as a user, you specify the growth increment. So every time we grow the crack, remember the low cycle fatigue example where we load, unload, and grow. So you specify a growth increment, which means the growth speed. And then for each and every crack, say you have 2D cracks, you have a number of crack tips, the one with the largest loading will grow with that specified, and the other ones will be scaled down. And if you use direct growth, we use the largest current energy release rate for the scaling, because the growth in this case is instant. So as soon as you determine that some they should grow, they will grow, all the tips that will grow will be scaled for this. And if you use fatigue, we use the delta K, which is the change the max minus the minimum stress intensity that we collected during the fatigue cycle. And that one is used for scaling. So a large delta K will grow faster than the one with small delta K. This is an example, the user guide 235 from the 2014 release. So we have a bracket of some kind, and at the top we have a pin, the red cylinder near the top with an arrow. That's a rigid pin, and we put point force on it, and we just oscillate that force up and down. And the force is closer to one end of the bracket. So if you look on the right-hand side, we see that the crack, well, I should say we initiate one crack in each flange of this one, equal size, and we let them grow both. And the one which is closer to the force, as you see now, it grows faster. The other one, the increments are scaled down, and the first one grows through, and the other one picks up speed. And this way we can predict that one will reach the boundary first, and the other one will continue to grow until it also hits the boundary. So this is an important phenomenon that we want to be able to model. Similarly, if you have a 3D crack, all the nodes along the front will not grow with the same amount. You start out, for instance, with a cylindrically shaped crack, and then unless everything is uniform, along the length it will grow in different speed. Because the shape of the front will typically grow from, say, a cylindrical shape into an elliptical shape or something like that, or any shape at all, and we want to be able to predict that shape. So what we do, Marc, is to scale the growth not only between cracks, but also along the front for each 3D crack. And similar to we just showed, we based it on the largest energy release rate for direct growth and the largest delta K for fatigue. And the scaling is based upon power law, so the current delta K, say, over the delta K max to the power of an exponent that you specify, or the scaling is based upon the fatigue law, say the exponent used in Paris law, for instance. And to illustrate that, we have user guide example 236. This is a block, I should say, with 3D tetrahedrals. And we have two cracks, cylindrical cracks near the bottom of the hole, one in each side, one is larger than the other. What we expect here is that cracks should go much faster through the thickness along the hole than it should grow, to the left and right in this picture. And that's what we see here. It's much faster through the thickness, and then it should tend to become straight as it continues to grow. Now we stopped it early, so we didn't see much more happening. But this effect that we see the shape going from a cylindrical now into more and more elliptical is we can get that by this scaling. And we can control how aggressive this scaling should be with the exponent. Next item here is the high cycle fatigue, how we do the cycle count, which is a very important aspect of the fatigue. So what we use is Paris law, and the simplest form of Paris law is shown to the upper right here. So the change of crack length with the number of fatigue cycles is just this expression with delta K. Standard good old Paris law. If we know how delta K varies with the crack length A, we can easily integrate that one. So if you look at the curve, the blue curve, which would be how delta K would vary with A, in general, we don't know that. That's part of the solution. We want to obtain this curve, actually. Delta K is a function of A for a given crack path. We don't know the blue curve, but we need to know the variation of delta K in order to estimate the number of fatigue cycles. So What we do, the process, we are at crack length A1. We had just done our representative load cycle. So we know the delta K at length A1. We grow the crack to A2. So we use one of the mesh updating methods I just showed to update the crack. We do another representative load cycle and get another delta K. Now we know delta K at A1 and we know delta K at A2. If we know, assume a linear variation, the dashed curve, and then we can integrate Parrish law. And that gives us the high cycle fatigue count. So it's kind of a post-processing done on the fly as we do the analysis. And the difference A2 minus A1, that's the growth increment that you as a user specify. So we calculate the delta Ks. From that, we can integrate Parrish law and get the cycle. So what we use is the plain vanilla Parrish law, if you like. You may want to use a more advanced one, for instance, famous Nastro equation, which is an extension to Parrish law, standard Parrish law, where you have more terms that take different things into account. And you can easily code that in Fortran in a user subroutine and use that instead of standard Parrish law using the same procedure. You may also want to take into account the spectrum load. So suppose your load looks like the red curve here. From that, you would create your representative load cycles. And then you can do a rain flow count of your real load. And when we're in the loop to integrate Parrish law, or the fatigue law, I should say, we can use these rain flow count results for scaling every load level you have. And this way you can take spectrum load into account. This is also done through the user subroutine today. Okay, let's move over to direct growth. What we do then is, as I mentioned, pretty different from the fatigue. We typically do a transient analysis, and when we fulfill the growth criterion, we grow the crack. And we have 5 growth criteria today. You use the total D or each mode separately, etc. All power law, etc. So these 5 methods. Important thing here is that the total amount of growth is not known. That's part of the solution. You want to find, if I load this just above so I go above the growth criterion, then I want to know, does it grow a finite amount? Does it grow through the whole section or something like that? And since this is not known, we need to use, or we do use an iterative method to find the total amount for a given load level. So when you get growth, Marc will redo the same increment with an updated crack length at the same load level and continue doing that until either the crack is deactivated because it reached the boundary or the growth criterion is not fulfilled. So you get a maximum K, say, larger than maximum G, smaller than GC. And this small amount that we grow each iteration is what you as a user has to specify. It's very hard in general to figure out what an appropriate amount is, so you have to specify it. You specify too small, you need a very fine mesh to resolve that small amount, and you may get into a number of iterations. And if you specify a too large amount, you may overshoot the actual solution. So here's an example. It's the same one I showed before. You have a crack in the center, which I use an option to force it to remain in a plane so it doesn't bend off or something like that. And the red parts here are rigid bodies used to pull it apart. And since we just pull at the ends like this, the growth will be stable. So at a certain load level, it will stop, and then we can increase, and it will grow somewhat more. So here are the results. On the left-hand side, we see the focused mesh, same as we saw before. And on the right-hand side is the same thing, just an outline plot. And we see also that the crack starts out straight and it becomes curved thanks to the scaling along the front, because the energy release rate is somewhat smaller at the ends where it reaches the boundary. The crack is at the boundary, and you have a smaller value there, so it should grow faster in the center than at the ends. And we very nicely capture that effect here. So moving on to crack initiation, we have three methods basically. We can make a cut in the mesh into the shells. We can split up the mesh, and we can use remeshing. You can make a cut. You see on the left-hand side here, the red curve, or red line rather, defines where the cut should be. So that's your input, just a line. When Marc does the initiation, it creates a cut in the mesh, and in the center that it's changed the mesh, shifted nodes, etc. And to do an outline plot, we see it was actually split up. If you use the mesh split up, you select element faces in 3D. On the left-hand side, we see this key section thing where I took out the center portion of the element, so we can see the element faces where we define where the crack should be initiated. What Marc will do is we'll look at this blue area and split up the mesh there. And on the right-hand side, we see that gave us two crack fronts. And this is the one we saw before. We start out straight, and then we can continue to grow it after initiation. With general remeshing, we define a surface. And in this case, we use an analytical surface, which is made up of triangles. So it's a triangularized surface, or a faceted surface, as we call it. It's just a mesh geometric surface. You can create it in Mentat in various ways. And the intersection between this surface and the mesh defines the crack. So these faceted surfaces, this is just simple circular discs, you can put them anywhere. Wherever they intersect the mesh, there will be a crack. It could be entirely inside, it could be like this, partly outside. And when we remesh, it creates a crack, just like we do with growth, we do with initiation. And we can also here have a focused mesh around the new crack fronts. And here's an example of a crack growth. This is a rather large wing structure with a mixture of shells, solids, connectors, etc. And you see a small part in the center, which is shown larger on the right-hand side. That's where we will have a crack. And this is the only part of the whole structure which is actually remeshed. And this one is then glued to the rest of the structure, and it's also connected with connectors, connector elements for the holes. So this is an outline plot of this section, this part of it which is being remeshed, and we have two cracks near one of the holes. That's the initial cracks. And what we want to do is to find what's the shape of the cracks. We could also do a high cycle fatigue analysis of this one, of course. So here's the simulation. We see we pull and release, and the crack on the left-hand side very quickly became straight and reached the boundary, and then it's deactivated. The other one has a much longer way to go. It successfully goes through that step, the sharp step at the bottom. It's a tricky situation, and it continues to follow through the structure. And you see on the right-hand side, when we did this model, no one anticipated that we could grow it this far, so it's actually glued on the right-hand side to the rest. And to continue an analysis, we need to make a larger chunk of this one grow through. So this shows that we can successfully do a crack growth analysis in complex geometry. Finally, a few slides on delamination. I have this simple example, and maybe I should show this first. It's the same one I'm used throughout. So it's two parts. All the nodes are shared, and I pull the center. That red thing is a rigid body here again. And we have two materials, and we want to model delamination between them. Previously, we had this, we initiated a crack, we defined crack faces where we would want to crack. Now we want to use a stress criterion to determine where this should be split up. So the delamination option of Marc is based upon a stress criterion. It looks at the interface stresses between two materials. So you have the normal stress and tangential stress, and your failure criterion is the normal stress over user-defined limit plus the tangential stress, etc. And if this expression is larger than 1, we will say this is failed, and we will split up the mesh. So in this case, where will it fail? Well, we pull in the middle, so just because we want to have a delamination in there, we can plot this delamination index. This particular increment 2, it's 0.86. And as soon as we increase the load and it goes beyond 1, we will fail it, we will split it. So when we split it, we break up the mesh, and then you have 2 options, or 3 options actually. You can either just continue with the stress criterion, which is a bad idea because once we split up the mesh, we have a crack. So what you have are 2 options here. You can activate crack growth with DCCT on the left-hand side. So the arrows show the local crack tip system. So you will get this region. So this will be one crack front, which is square shaped crack front, and let it grow. Or you can fill that gap where you split it up with interface elements using a cohesive zone material model, and continue to use the stress criterion on the region outside the interface element. And this will show up like this. So the elements in pink are the standard X elements, hexahedral elements. Element 188 is the interface element, the green one. So whenever you start out without any interface element at all in the model, we create it on the fly inside Marc. So we see that it starts to grow, and in the middle they disappear because we can also deactivate the element when it's full failure, so it doesn't take any load at all. And that concludes my presentation. Thank you very much. We should switch over to Q&A.